Hello everyone, this is Yash Kumar, and this is the third part of my PyCaret uh, walkthrough series. So, in the first two parts, we went over what PyCaret is and how we can use it to solve different data science problems. The first one I focused on classification and regression. The second one I focused on um, clustering. Um, Anomaly detection and association mining. But in this third and final part, I'm going to be talking about time series. So I split this into two different Jupyter notebooks or Google Colabs. And so the first one, I'm going to be speaking about time series forecasting without exogenous factors. And for the second one, I'm going to talk about with exogenous factors. So exogenous factors are nothing but like external factors that we cannot control. So yeah, let's get into it. So again, similar to how we have in the past, we're just using the get data method that PyCaret provides so that we can use the data sets that they have. The simple one for without exogenous factors is this one called PyCaret downloads, where it has like total number of downloads based on the date. And yeah, basically, we just do some bit of data manipulation at the start because the date that we have is no, it's a string and we want to convert it into date time format and then set it as index. So now it's like in the correct format. Now that we have that data, we're just setting some variables such as figure arguments, folds as in how many folds we want it to run, and fh, which I'll explain those a bit later, maybe once we get into the actual forecasting. But let's just say it's like that's the amount of data that we want to predict. Yeah, I mean, it is a test. Here you can see in the setup step as well, actually. The transform test set shape has 10 rows. So, yeah, I mean, that's as simple as it is that I could explain. Yeah. And at first, I just decided to plot the data. So we have all of this information, and then we created a periodogram which maps the frequency of the whole thing. And yeah, as you can see, like there's different frequencies for different values, and we can just do diagnostics, which is just a whole set of graphs that you could create, as well as difference plots. So these are basically all different types of plot that we're creating to get some idea. So this is an interesting one, classical decomposition. I think in this one we're seeing like this is the one I wanted to bring some attention to. So as you can see, there is some seasonality to the data. I think we can even observe that while we're looking at this graph. There definitely seems to be like at least, if I'm correct, I think it looks like about a week where we're getting some seasonality. And yeah, so that here as well, the seasonal period is 7, which is completely accurate. You can see that. Uh, yeah, another cool thing is that it's able to split it into a train test split. Like you can plot that. So this is the training data until here, and the orange one is the test data that we have. And another pretty cool thing that you can do with time series is you can call this check starts method, where it brings up all different types of statistics, such as p-value, white noise, stationarity, so on. So yeah, one thing to notice here, I think, is that the stationarity is false, basically that the data is not stable. Um, Stationary. Wouldn't say stable, but more so stationary. Yeah. Um, so we want to forecast this data, right? But we don't have the, uh, I mean, I wasn't sure what all models were available. So again, we're just going back to the classic TS models. Excuse me. And yeah, it just gives a list of all the models that are available under this that we can train it on. And yeah, I mean, uh, I just got compare models to see which one is the best one, and it shows XG boost, extreme gradient boosting with condition seasonalize, and detrending. So that is the model it decided to go with. And when I called predictions, it created some predictions for our test data, and then we can see compared to the actual data how it's performing. So XGB regressor isn't too bad. You could see it's close enough to the data. It definitely isn't perfect by any means, but it's creating a trend which is reasonable. So the same thing I just did, as we just did with XGB regression, I just do the same thing with AutoML. And again, just when you forecast it, it also has like prediction interval. So the blue line that you can see is its predictions, and the interval is some sort of extra information that it's giving that it could be within this range of the data, which covers the actual thing quite well if you see. And yeah, I mean, if you just plot it for like a couple extra dates when you set FS21, it just plots beyond the data set that we have. So you can see it maintains that seasonality within its predictions as well. So this is what we are ultimately trying to do, emulate what from the data that we have and predict the data that we do not have. And yeah, another cool thing is that when you call compare models, you can also pass this particular attribute, which is nselect, which basically gives you a list of three models in this case. So the top three models will be the ones that you return. And yeah, I mean, there's some extra steps that we're performing, but ultimately what we want to do is we want to blend these models and predict using that. So um, to be fair, that isn't predicting as well as XGB might have done on its own, but then that it does come out across around 0.8581 MAC, which isn't too bad again, as you can see in the graph, which it is quite decent estimation of the data, but we definitely did better earlier, I think, in my opinion, with this one, where the predictions also look very accurate. So yeah, I mean, these are just different things you can do when you have the uh, time series forecasting as a problem. But this is pretty simple because all we had was a date and the data that we want to predict. But there might be cases where there are exogenous factors that I was talking about. So for this one, I decided to go with air quality data, which again is the same as the tutorial one that PyCaret provides, but it is the only one I was able to figure out that I had access to. And then again, so what we're trying to predict is this CO. I mean, this particular column is what we're trying to predict. And yeah, I mean, again, similar to last time where we just had date. Now we have date and time, so we're combining that to create our index. And again, there are some cases where, as you can see, the data that we're trying to predict is not accurate. So minus 200 is apparently the default value for this data set. And what we're trying to do is, since these are not accurate or helpful, we're just dropping these entirely. So as you can see, we're just dropping them to give np.nan. And I mean, this is just part of the regular cleaning process that we do. And again, so since this is like a hourly data set, we want to predict 48 hours for our data. And again, we set up the whole thing and we're able to plot the model. When you call plot model, it's plotting everything against time now because the index was set at time. So it's just plotting everything. So one of the interesting things to note here is that HC column does not have data for a lot of input. So it's kind of not useful, right? Like if you don't have data for the entire period, it's kind of uh, not that useful. Let's just put it that way. So what we have done later is excluded it, as you can see here. But before we get into that, another cool thing is that while you're displaying, if you just add like a display format of plotly dash, you're able to zoom in, pan out, and all sorts of things. So Yeah, I'm still getting the hang of it, but basically, if you zoom in a bit more, that's when you'll be able to see that there's some sort of seasonality. I mean, we knew that already as well, but it's a bit difficult to show on this one, and especially on this one. But yeah, ultimately, what I'm trying to say is there's definitely a seasonality that is forming over it between the today and next day. So there's a periodical format that the data is displaying. Knowing that we are also drawing this correlation plots, and as you can see again, like a lot of these factors seemingly have a lot of similar trends. So especially like within the first five, you can see a lot of these have a very similar how do you say, time series visualization. And yeah, I mean, another thing is like AH, which I think is something to do with air humidity, if I'm not wrong, and that's pretty much a flat line. So it's not really having much of an effect on our target variable. Knowing this, we exclude that as well and we drop it. Now, again, we're trying to do this, but without exogenous factors. So all we're doing is we have the similar to the previous case where we just have COGH that we're trying to predict and the time, date time. And based on that, we have quite a lot when you do the modeling using ARIMA and everything. We can see like the prediction interval is quite sparse. Like it's not close enough to what we would like it to be. And yeah, so instead, what we want to do is like integrate these exogenous factors so that we can make precise predictions in the future, right? But then we include those, and it's much better comparatively, I think. Like this is almost within -5 or almost within 10. But this actually brings a different type of issue if you think about it. So now you have 10 external factors that you need to access every time before you can make a prediction. And that's not ideal, especially when we know for a fact in this previous graph that I was talking about that a lot of these have a pretty similar impact on it. This has, all of these have a positive correlance correlation. So, because these correlations are there, what we can do is we can drop these. So, a lot of them had very similar. So, we just took one of them, which is NOXGT. And then we took one which had a negative correlation, which is if I can go back again, excuse me. So yeah, as you can see, this has a positive correlation, but this has a negative correlation. So this was an interesting comparison compared to the rest of them. And with these ones, again, you can see like they have a very similar trend, just opposite of each other, and we just took one of them. So now instead of predicting 10 different exogenous factors, we're trying to predict only three. So we trim the data set to just the target, the index, and these three. And now with this, not sure why this is still stuck apparently, even though it has run, I'm sure. But anyways, ignoring that, yeah, once we train the model on these ones, we see that while the prediction interval has increased, uh, the variables that we require is a lot less now, and we're not losing too much of the data in that space. So with that data set, what we're doing is similar to how we're predicting the whole thing in the future, like the target variable, we can also predict the exogenous variables. So we're trying to model these variables individually. So index versus NXGT, index versus RH, and so on. And this is what we're doing, where we're basically setting up all these experiments and training a model for each of them. And ultimately, that's giving us each of these models, which can be used to predict the future values of these exogenous factors. And using these exogenous factors, then we're creating a prediction model for our main target variable, which is air quality. Now, which you can see has come out of something like that. So again, these there were a lot of steps in that, but like the ultimate thought process is that we want to predict our target variable against the time, right? That is the essence of time series visualization. But when you have external factors, what you can do is predict those external factors individually and then use those to integrate and make the final time series predictions for a main target variable. So, yeah, I think that's about it. And I hope that was quite helpful to anyone who might have gone through it. and hope this series makes you get started, get your hands dirty on PyCaret. And thank you very much for watching.